became more and more of a crisis in physics to understand what matter was like, because it looked so obviously right that it had to be electrons going around nuclei, and yet nothing worked when you worked it out. And the discovery was made then in the discovery of quantum mechanics, first in the behavior of light and then in the behavior of matter, and finally culminating in 1926 with the full equations of quantum mechanics, which told us that the laws of motion of Newton were not right and had to be modified to other laws, which are quantum laws of motion. And when this quantum laws of motion were applied to electrons to explain the properties of matter, it was a fantastic success. The properties of the atoms can be all worked out mathematically, in principle at least, in the simple atoms in detail. And therefore, the theory behind chemistry, which atoms combine with which, at what rate, and so forth, is in principle. Theoretical chemistry deeply is physics. It's not a joke. It's the chemist will admit that's exactly his point of view, that the understanding of the atoms in the deepest level is physics, except that the atoms have so many particles in them, it's very hard to calculate what's going to happen. So he has to use a lot of empirical rules to help him. But as far as we can tell, there's nothing about chemistry that's not understood ultimately as the behavior of electrons following the laws of motion of quantum mechanics. This defines the properties of all substances also, and so that the whole theory of the properties of ordinary substances and the chemical properties and so forth have all been reduced to the motion of electrons. In the meantime, the theory of light and its interaction with matter, which was Maxwell's equations, had to be modified to become a quantum theory also. Oh, I forgot to mention that during this time, somewhat to one side of the way I want to go in these lectures, I'm not going to discuss much about relativity, but the theory of relativity was developed, and that just makes it easier for us to guess laws. It tells us if we know how something varies in space, then we know how it varies in time, or vice versa. That there's a nice relationship between the behavior in space and behavior in time, and that it's all sort of different aspects of the same geometrical thing called space-time. At any rate, Dirac, using the principles of relativity and the new quantum mechanics, found a wonderful theory, as simple as possible thing you could write down for the motion of electrons, Dirac's theory of electrons, and that was the situation about 1927 or 8. But the problem of the interaction of electrons with light, which was a complete quantum theory of electrodynamics, in other words, make Maxwell's equations of light, of electricity and magnetism, and the theory of motion of electrons, all into one grand theory, was accomplished in 1929 in the theory that was called quantum electrodynamics. Trouble with it was nobody could figure anything out, or better. When they did figure it out, they got nutty answers. If you didn't do it too carefully, you got a reasonably good answer for a problem. But if you carried it out very carefully, you would get some silly answer like zero or infinity or absolutely absurd results. This strikingly lasted for 20 years while people tried to figure out what the correct theory was. During this time, experimenters were measuring things more and more accurately. The theory of they found a few things with very subtle effects that the theory of interaction of light with electricity should explain. And then they measured them, and they found these effects, but they couldn't explain, that is, the theory didn't explain it quantitatively, because when the people made the calculation, they got infinity instead of the right result. As an example, an electron in a magnetic field precesses at a certain rate, and the rate, according to Dirac, was a certain amount. But he didn't take into account the interaction of electricity and light. And when he took it into account, we knew that the answer should be wrong. Let's say that Dirac's answer was right, but when experiment was made, it came out not to be 1, but to be a little bit more. This number here, the experimenters weren't good enough to tell us exactly. It's somewhere between 5 and 21 here. We write it as 8, plus or minus 3 as the next digit. That means this is not measured accurately. So by 1948, 20 years, we had at last measured something which showed that the original theory was without interaction is incomplete. This is supposed to be the result of interaction. When you went to calculate it, you got infinity. So there was a very strong effort made then in 1948 because of the fact that experiments were showing such accuracy to try finally to get that theory straightened out. And it turned out, surprisingly, it was worked out more or less independently by three guys who got Nobel Prizes, one of which you see here. And Professor Schwinger, that's not me, but one of the other ones, first worked out a correct way. We found out that the original theory that was written in 1929 by Heisenberg and Dirac and Pauli was very nearly correct. And the problem was that there was something wrong with the way they handled doing the calculations, and we straightened it out. And then we could do calculations, and Schwinger, for example, calculated this and found out that it was something like this, theoretically. And that was a tremendous achievement. It's a great excitement, because that meant we really understood more subtle details, and that the original theory of Heisenberg and Dirac and so on was fundamentally right, just a little switch on how you calculated things. Now this is the theory, then, that we're going to talk about. This theory has lasted now for 50 years. 30 years. I can't add. From 1979, 1949. Oh, it's 50 years, yes, from the time that Dirac and Heisenberg wrote it, and it took 20 years to figure out how to calculate with it. Then the remaining 30 years, the methods of calculations improved. They calculated things much more accurately, and the experimenters became more and more adept at measuring things. And this particular rate that they measured in 1948 to here, now in 1979, has been measured to be, in fact, 100.11596524, and the 4 may not be 4. It could be somewhere between 2 and 6. After all, the more you write it, somewhere you have to stop, right? And this, I write to show you the tremendous achievement of experimenters during the last 30 years in order to test with the precision the correctness of the theory. In the meantime, poor guys using calculators and sweating and writing marks on pieces of paper. So I'm calculating the results of the theory under the same circumstances for the same phenomena, produce a predicted value that it should be 6523 within plus or minus 3. Why should the theories have a plus or minus? They get exhausted in computing the number of decimal places that they need to keep up with experimenters. This is not atypical. There are 2 or 3 or 4 perhaps different places where it's been measured and checked to that degree of accuracy. This degree of accuracy, that number of decimal places, corresponds to a precision something like this. If you were measuring the distance of me to the moon, the question would come up, do you mean from my chin or from the top of my head? The difference between whether it's from the chin or the top of my head to the moon is the plus and minus 2 on the end of that number in proportion, all right? That is to intimidate you that the theory is correct in high accuracy. I don't need to produce a large number of other experimental results. They all have this feature. It is remarkable that at this time it is possible to say that there's no experimental discrepancy known between the predictions of the theory anywhere and the results of experiment. It doesn't mean we can compute everything. The rules of the game by which we make the computation, the laws underneath everything that makes nature work, are simple. It doesn't mean we can really figure everything out. To give an example, if you play the game of checkers, I think you call it checkers here, maybe draughts, something. The rules of the game are very simple. The way the pieces move is simple. And if you want to make it even simpler, make the rule no kings. But when you come to the end of the board, you start at the beginning. It doesn't make any difference. The rules are simple. But imagine a checkerboard with 100 million piece squares on each side. Hundreds of millions of these checkers in different positions moving through the board, taking pieces and being taken from the other. Which way are they going to swirl? Which way is the game going to go? That takes a lot of thinking. It isn't the difficulty of the rules that's involved, but the multiplicity of its action and interconnections. Matter, as you all know, is made out of atoms and all that stuff, is such a multitude of little particles that in ordinary circumstances, so much is happening that in spite of the fact that the rules are relatively simple, not quite as easy as the checker rules, but pretty easy, it still is very difficult in almost all circumstances to figure out what's going to happen exactly. But when we can't figure it out exactly, but can do a pretty good job of approximating, the phenomenon is in the range that we expect. When we have a situation that's sufficiently simple, a corner of the board where there's only a few pieces, then we can compute exactly what ought to happen, and when we do experiments in those circumstances, it fits exactly. And that's all we can say at the moment about this theory. This theory has been designed, was originally designed in the ideas of space and time and a geometrical framework. And the question is, how small a scale can we go down to? And during the time of this period of time, we not only tried to measure accuracy, but also tried to see how small a distance the theory would be correct at. And I can only tell you the distance is 10 to the minus 15 centimeters. That means 15 zeros before you get to 14 zeros, before you get to a first digit of distance in centimeters. That thing is that accurate. We know that the laws are that accurate. To put it another way, it used to be thought that atoms were small. That was a limit of measurement. But at the present time, with the new instruments and design during all this time, we've been able to make instruments that can test this theory down to distances that could be described this way. If the atom is made 100 kilometers on a side, then we're measuring with 1 centimeter accuracy inside. So the theory is right. The distances correspond to a centimeter when an atom is 100 kilometers. So altogether, I can only emphasize with delight and excitement the fact that so much of nature is so accurately describable by one theory. It's an enormous range of phenomena, all the things you ordinarily see. The best way to describe what the phenomena are, colors of things, the softness of materials, the weight of things, the way their temperature, when you change the temperature, how much heat it takes, and sounds, and all these phenomena. The only best way to describe is to describe the phenomena that are not included in this theory. And one of them is the accelerations produced by gravity. The force of gravity is in another theory, gravitational theory, or general relativity. Another range of phenomena have to do with exciting the interior of nuclei, nuclear physics, protons and neutrons, radioactivity, and nuclear phenomena. That excluded, all the rest of the phenomena of nature are contained in this one theory.